is same. Everywhere potential is equal, right? So those surfaces are called equipotential surfaces. Generally, equipotential means equal potential. Okay, the locus of all the points. Locus means it is the collection of all the points in a medium at which electric potential remains the same. So where electric potential is same, so collection of all those points form a surface, and those surfaces are called equipotential surface. Now let's talk about properties of equipotential surface. No work is required to move a charge from one point to another on an equipotential surface. Generally, when we talk about potential difference, what do we say? Potential difference means one point is at higher potential and other point is at lower potential. So if both the points are at same potential, so there is dV is zero now. And what is dV? dV is work upon charge. So work done in bringing the charge, work done per unit charge, right? In moving the charge from one point to another in the electrostatic field of given charge, then we find potential difference. But what if potential difference is zero? What if we have equipotential surface? What if potential is same everywhere? Then no work has to be done by the charge. Okay. Charge has to do work when it moves from one surface to another having different potentials. One point to another having different potentials. But if both the points have the same potential, then no work has to be done by the charge. Charge can move easily. Next is no two equipotential surfaces intersect. Okay. Yes. The direction of electric lines of force or direction of electric field is always normal to the dl of the equipotential surface, that is E is perpendicular to dl. We will discuss about all these points in detail. Don't worry. So when we draw lines of force, then lines of force and equipotential surfaces, they are always perpendicular. And for an isolated point charge, the equipotential surface is a sphere. As for a point charge, we take equipotential surface is a sphere means, because if we take all the points, sphere carries infinite number of points, right? Sphere has infinite number of points, and this is the center where the point charge is, and we are saying that it is the sphere. Equipotential surface is a sphere. It means that from this charge, all the points on the sphere, they are at equidistant. They are at equidistant. So when these points are equidistant, then everywhere we have the same potential. So collection of all those points, right, which have the same potential, forms the sphere. Are you getting what I'm saying?
Yes, ma'am.
क्या बताया मैंने?
मैम एक स्फीयर है इसमें बहुत सारे पॉइंट्स हैं और उनके जो इलेक्ट्रिक पोटेंशियल है वो सेम है.
जैसे अगर ये सेंटर पे चार्ज है, तो मैं ये बोल रही हूँ कि वी हैव दिस चार्ज, ठीक है, वी हैव दिस चार्ज एंड एट अ डिस्टेंस ऑफ 2 सेंटीमीटर, इफ वी से at a distance of 2 centimeter, what is the electric potential? Then you can easily find electric potential as kq by r. Yeah, we know the value of k, it's 9 × 10⁻⁹. We know the value of charge. We know the distance is 2 centimeter. So by putting all the values, you can find the electric potential. And if I say that find electric potential in this direction at a distance of 2 centimeter, again, you have the same values, right? If I say that find the distance, find the find the potential at this point, and this point is also at a distance of 2 centimeter. Again, you'll get the same potential value. If I say find the potential at this point, which is at a distance of 2 centimeter, again, you'll have the same potential. So everywhere from this charge at a distance of 2 centimeter, you will find same potential. Okay, and if we collect all those points, if we collect all these points in 3D, right? If we collect all those points, then a sphere will be formed. So sphere is the equipotential surface for an isolated point charge. Inside a hollow charged spherical shell, the potential is constant. This can be treated as equipotential volume. No work is required to move a charge from the center to the surface. See, at the center, electric field intensity is 0. And where intensity is 0, their potential is constant. Because E is minus dV by dr we had done. We had done the differential form and the integral form, right? In differential form, we write electric field intensity as dV by dr. So differential of a constant is 0. So where we have no charge, the point where we have no charge, their electric field intensity is 0. So inside the hollow charged spherical conductor, there is no charge. No charge resides inside the conductor. This we had done in the previous chapter. Whole charge resides outside the conductor. So if there is no charge, means no electric field. No electric field means dV by dr is 0. Differential of anything is 0. Differential of V is 0. Therefore, V is a constant. We'll discuss this as well in detail also, don't worry. So in a uniform electric field, any plane normal to the field direction is an equipotential surface. Okay. The spacing between equipotential surface enables us to identify region of strong and weak fields. So equipotential surface for an isolated point is like sphere. So we can draw dotted lines. See this solid lines, you can see if we have this charge, these solid lines represent the electric field lines, electric lines of force, right? So when we draw electric lines of force for a positive charge, then those electric lines of force are always directed away from the charge. So these solid lines, these arrow lines with arrow represent the electric lines, okay, electric lines of force. And these dotted lines represent the equipotential surfaces. So you can see if we have a charge at the center and this distance is 1 centimeter, then at 1 centimeter, wherever you go at a distance of 1 centimeter from the center, you will find the potential same because it's kq by r. Na?
Yes.
R is 1 centimeter everywhere. Q is also constant. K is also constant. Here in this case, value of Q is given, right? So we have the same value of potential at every point. So we can collect all those points, we can join all those points and we'll get this equipotential surface. In the same way, if we move at a distance of 1.5 centimeter from the charge, the second line, second dotted line you can see. So everywhere you will have the same potential value. Okay, so this is another equipotential surface. And if we move at a distance of 2 centimeter, let's say, so everywhere at a distance of 2 centimeter, you can see, look at this arrow, look at the cursor. So everywhere at a distance of 2 centimeter, we have the same value of electric potential. So the third line, dotted line, is again an equipotential surface. Okay. This is an equipotential surface and this represents electric lines of force. This we have discussed. So equipotential surfaces for a pair of similar point charges. So, okay. This is how we draw equipotential surface for a pair of similar point charge. So for two identical positive charges, this is the equipotential surface. Now we have a question. The potential due to a dipole depends on. We have discussed dipole. And what is the formula of potential? Srishti, you can also respond. What is the formula of potential? V is equal to Kp cos theta by r square.
By r square.
Yes. Kp cos theta by r square. So this potential, P is what? P is Q into 2A, right? Charge into the distance between the charges. So potential due to a dipole depends on position vector. Number 1, angle. Number 2, dipole moment vector. Number 3, all of the above.
All of the above.
Very good. All of the above. Next question. The work done to move a charge on an equipotential surface is 3 joule, 2 joule, 0, 4 joule. When we have potential same everywhere, then
0.
yes.
0.
Okay, if I say that we have a source charge, okay, and this is the field of source charge, and we have a test charge here. Okay, so this charge is at infinity, it comes to point this, and let's say that it does some work of, for example, 10 joules. So work done in moving a charge from infinity to some point A or P, whatever it is equal to electric potential at that point. This is how we find work done. Sorry, electric potential. So electric potential at point A is equal to work done in moving the charge from infinity to point A. Okay. Similarly, if this charge moves from this point to some other point B, then we can write work done in moving the charge. This is from infinity to A and this is from infinity to B is electric potential at B. What if this charge wants to move from A to B. Then extra work has to be done. Suppose here in the previous situation, work done is 12 joules because you can see that charge is closer. Now B, this point B is closer to as compared to A. So this charge has to do some extra work to reach there. So if this charge is already at A, assume a situation where this charge is already at A and this charge moves to point B, then this charge has to do some extra work. Where is the cursor? So this work done in moving the charge from A to B is equal to potential difference. Potential difference is electric potential at B minus electric potential at VB minus VA. Okay. What if we have this charge and at some distance R? Suppose this charge Q naught has to this charge Q naught comes here at some distance R from this charge. So electric potential at this point P due to this charge will be KQ by R only. And suppose we choose another point Q and Q, let's not take Q, let's take this point as R. Okay, and now this time again this distance is the same R. So this charge has to do the same work in reaching point R. Because both the points are at equal distance from the charge. Right? So what is VP? VP is KQ by R and VR is also KQ by R. So you can see that VP is equal to VR. VP is equal to VR. Because they are at equal distance, Q is fixed. For this particular case, R is also same and K is a constant. So we find that all the points which are at a fixed distance from the charge, their test charge has to do the same work, same amount of work. If this charge comes at point this, again this distance is R. At this point also charge has to do the same amount of work. Okay. So everywhere charge has to do, let's say, X joule of work done. Everywhere X joule of work done, work will be done by the charge. Okay. So if a charge at P wants to go at R, then no extra work has to be done by the charge. क्योंकि ऑलरेडी उसने उतना अपना होमवर्क करके आया वो एक्स जूल का, और यहाँ पे आने के लिए भी उसको एक्स जूल ही वर्क डन करके आता, तो वो कहीं पे भी इस पॉइंट पे चला जाएगा अगर, तो नो वर्क विल बी डन बाय द चार्ज. And we can see all these points are at equal potential. And when we collect all these points, so locus of all these points, collection of all these points form an equipotential surface. Okay. So work done is 0. And one more thing, we can prove this using a relation, mathematical relation between work. See, we know that work done is F dot dl. Yeah, yes?
Yes, ma'am.
And F is Q naught E dot dl. Yes? Okay. And for a point charge, we can consider this Q naught as, sorry, for the test charge, Q naught can be considered as unit positive charge. So we can write work done as vector E dot vector dl, or this is EDL cos theta because this is the dot product, right? So on equipotential surface, everywhere work done is 0. Work done is 0. Yes, this implies EDL cos theta is 0. Or we can say cos theta is 0. At what angle cos theta is 0? 90 degree. At 180 degree cos theta is minus 1. At cos 90 degree it is 0, no?
Yes.
So at cos 90 degree we have this 0.
Yes.
So it means that both E and DL, they are perpendicular, right? So from here we can conclude that equipotential surfaces are always perpendicular to the field lines. Okay, let's draw electric lines of force first for a uniform electric field. See, you can see lines of force are equally spaced. Okay. Now, how do we draw equipotential surface for a uniform electric field? This is positive end and this is the negative end, because for a positive charge, lines of force are always away from the positive charge, and for a negative charge, lines of force are always towards the negative charge. And always perpendicular. This is not drawn as it is perpendicular line. So let's drop this. All lines should be, when they emerge, they look perpendicular at the point of contact. Yes. So this angle should look 90° every time when you draw an electric line of force. Okay. So how do we draw equipotential surface? So as we have discussed that equipotential surface, they're always perpendicular to the electric lines, electric field lines. तो कैसे ड्रॉ करेंगे इक्विपोटेंशियल सरफेस बताओ कैसे करेंगे ऐसे so these are equipotential surfaces. This is electric lines of force. Okay. And these are equipotential surfaces.